and let us begin. All right, let's see. So here we are, June 8th, 2016, and we're going to start with problem 2.4 from the Beer Vector Mechanics book. Let's see, so let's make this. And all right, so what we have here is we have two structural members, B and C, are bolted to bracket A. Knowing that both members are in tension and that P is 6 kips, so P here is 6 kips. What's a kip again? Good, 1,000 pounds. And knowing that Q is 4 kips, determine graphically the magnitude and direction of the resultant force exerted on the bracket using the parallelogram law and the triangle rule. Okay, so how might we do this? Well, I'm not going to be able to do an exact solution to this on a PowerPoint like this. To do this quite accurately, you would instead need to use a to actually do it truly graphically. You would need to use proper tools. You would need to use a ruler, a set of graph paper, and a protractor. So if you really want to do a true graphical solution, you can, and you can produce an accurate solution to within 1 or 2% using graphical methods, but you have to use the proper tools. You can't hand sketch this to really do a accurate graphical solution. So what do I mean by this? So let's look at option A, part A. I want to get the, so basically I have two forces on here. Now, truth be told, these are, we could actually get into the, later on, you could get, in later courses you may learn that in reality these aren't, exactly purely point forces, and that you can really study in detail the actual interactions of the bolts and the connections and all this kind of stuff. But for our purposes here, we'll treat these as 2 point loads interacting at this point of coincidence here. So say we have force, essentially what we have is we have force P here, at an angle of 25 degrees, which is 6 kips. And on the same point, we have a force of 4 kips at an angle of 50 degrees. So how would we do these graphically? Well, if I wanted to do these graphically, what I could do is I could say, okay, for the parallelogram method, again, the parallelogram method states that the resultant will be equal to the diagonal on the parallelogram. So what I could do is I could have force, again, I would want to arrange these tip to tail. So let's start off with Q here, or we could start with P, it doesn't really matter. So we could say P here, which is, Q here, let me erase that.
That's what asked you to do, use the parallelogram law or the triangle rule. Would it matter?
Well, there's two different methods here. We can do one or the other. But again, it's graphical. They kind of reduce the same thing in many ways. But anyway, so this is actually going to be Q at an angle of 50 degrees. And then P here would be, it's difficult to draw this. Again, to draw this accurate, we're not going to be able to actually get a solution to this graphically just using a pen and paper like this. You would actually have to use a, like I said, you would actually have to use a protractor and a ruler to do this with any kind of accuracy. So you do something like this. You'd set them up, one into the other, graphing them accurately with both their magnitudes and their direction. So for example, what I mean by that is, that would be P here, sorry, not Q. P, not Q here. So I would actually use a protractor and literally measure out that this is 25 degrees. I would use a protractor and literally measure out that this one here is 50 degrees. 25 degrees. And I would use a protractor to literally measure that this one here is 50 degrees from the horizontal. Like so. And I could also realize that if I went the opposite direction, the parallelogram here, if I put P first and then Q, that would be the corresponding opposite. P, then Q, I will get a parallelogram. And the diagonal of this parallelogram will be R. Again, we cannot do this accurately just using pen and paper. I do not have the tools in front of me right here to do this with any kind of accuracy. So instead, I'm just setting up a basic sketch to illustrate how you would do this. You would literally use a ruler and a protractor to do this graphically. So a triangle rule would be, so this would be a graphical graph using protractor. And I can just tell you now that I'm not going to ask you to do a graphical method on an exam. You do not need to bring a protractor to the day of the exam. I think that's a bit ridiculous. And ruler. Resultant is diagonal of parallelogram. That's a crude drawing of a parallelogram. All right, and the triangle rule. Well, we can simply make a triangle where it would just be something like this. Again, you'd have to graph it accurately. P, Q, and the resultant is the base of the triangle. And that's the resultant. Again, all you're doing is set up a triangle.
My biggest question for this problem was that there's that alpha.
On 4?
Yeah, 2.4. There's an alpha defined.
I don't think so. Where? This is 2.4 on the screen here. Do you have a different version of the book by any chance?
No. It's the same problem. It's just you end up with an angle of 3.8 degrees over the horizontal, I believe.
Oh, in terms of, okay, the magnitude and direction. Well, again, that if done graphically, you would simply measure the angle off of the horizontal with a protractor. Of course, you can also solve it rectangular. We could also solve it, I do not do graphical methods. I would not solve this graphically. This problem is just illustrating that you can do these graphically, but again, I really do not like graphical methods. They're not that precise. You need a lot of special equipment. Well, special equipment. A ruler and a protractor really aren't the most, specialized equipment in the world, but you don't really usually have them with you on an everyday occurrence. But your usual rectangular methods can be done with just whatever you have lying around. So what I might do instead is, would you like me to work through this using actual rectangular methods?
Yes.
Okay, that would probably be a bit more, accurate in my view. So let me do that. Okay, so slide. Let me delete these boxes here and here. So I'm going to solve for this using a method that I would encourage you to actually use on the exam. So today we are going to talk about the nature of equilibrium and what exactly equilibrium means. So some of the topics from today's homework and yesterday's homework did overlap a little bit there, but that's okay. So here, let's look at this. We want to find the magnitude and the resultant. So essentially, I'm going to draw a little free body diagram of the point where these two forces meet. I'm going to have a force P, which is going to be 6 kips at an angle of 25 degrees. And then I'm going to have a 4 kip force at an angle 50 degrees below the horizontal. 50 degrees below the horizontal. And that is a simple free body diagram of this system. And I want to find the resultant, which will simply be the summation of these two forces. So let's look at that. All right, so R, again, is going to be equal to P plus Q, fundamentally, in terms of vector notation. So I could say vector R is equal to vector P plus vector Q. But more importantly, Rx is equal to Px plus Qx. What this means is the x component of vector R is going to be equal to the x component of P plus the x component of Q. So Rx equals Px plus Qx. Note, I am using the vector sign above these to indicate that they have components. These will have x and y components. Meanwhile, these are components. These are not vectors. These are simply components, the x components in this case. So here, this is going to be, let's see, let me just remind myself that this is P and this is Q. So here, in this case, both P and Q are going to have negative x components because they're clearly both pointing in the negative x direction. Although, truth be told, that's completely arbitrary. When we set problems up, we can define our x and y axis however we wish, as long as we're internally consistent. If I really wanted to, I could define this direction from here to here as positive y, couldn't I? I could define this as the positive x-axis. It's totally arbitrary. But, you know, standard notation is we just put positive x-axis this way, positive y-axis this way, and call it a day. But in certain problems, it can be convenient to define your x-axis in other orientations. But anyway, one key for statics is that in order for something to be in equilibrium, it must be in equilibrium in every coordinate system. So you can always shift the coordinate system if for any reason it's convenient. Okay. Now, so Px, this is going to be negative 6 cosine 25. 6 cosine 25 degrees minus 4 cosine of 50 degrees. And this will come to negative 6 cosine of 25 degrees minus 4 cosine of 50 degrees. And this will come to negative 8.01 kips. Negative 8.01 kips. And then Ry. Now, note here, Ry is, well, first let me just say it's going to be equal to Py plus Qy. But let's note that vector P is going to have a positive y component, and vector Q is going to have a negative y component. So I will attach signs appropriately. So Py is going to be 6 sine of 25 minus 4 sine of 50. Minus 4 sine of 50 degrees. So again, where this comes from is the 6 sine of 25. This is the vertical component of vector P. So vector P has a magnitude of 6 kips and is at an angle 25 degrees above the x-axis. So it's 6 sine 25 with a positive sign here. Vector Q has a negative y component. That's why we have a negative sign here. And it has a magnitude of 4 and an angle of 50 degrees from the x-axis. So that's why it's negative 4 sine of 50 degrees. Let me throw that into the calculator really quick. Sine of 25 minus 4 sine of 50. And this comes to 22.29 kips. 22.29 kips. Oh, no, it does not. Sorry about that. That was bothering me. That was distressingly large. fat finger on the calculator. It is actually negative 0.528 kips. Negative 0.528 kips. Any questions on that so far? Okay. So now I have vector r. I currently have vector r. And so I actually could just declare that the answer, well, sort of. I have the vector, but I really don't have its, quote, magnitude and direction. Usually when I say magnitude, I'm talking about the size in polar form. I want a single value. I want magnitude of r, like this. And this is going to be equal to the square root of rx squared plus ry squared. And so this will be equal to the square root of 8.01 squared plus 0.528 squared. And this comes to this comes to 8.03 kips, assuming I did the math correctly. Oh, yeah, that's a little far from my taste. .03 kips. And so that will be the magnitude of vector r. Now, I need to find the angle of it. So what I'm going to do is I'm going to consider this. I realize this thing, vector r, is going to be in the third quadrant. It's like here.
How do you know it's below the horizontal?
Okay. Look at this. It has a negative x component, which means it's going to be somewhere to the left of the y-axis. It has a negative y component, which means it's going to be somewhere below the x-axis. And so this is going to be my theta here. And theta is going to be the inverse tangent of ry over rx. And notice, just like yesterday, I'm not going to mess with the positives and negatives when I'm getting the theta. I'm just going to realize what quadrant it's in and get the angle off of the x-axis and then just report it as that. And that way I don't have to worry about what the domain of the inverse tangent function is and all that nonsense. I can just get a result using positive numbers and report it as such, reported appropriately. 0.528 over 8.01. So inverse tan, that over that, and I get 3.78 degrees. Below, that's a W. Below negative x-axis. Alternately, you could also represent this if you wanted to. I've seen people represent it like this to indicate below the negative x-axis if you want. But I usually just write below negative x-axis, but you can use any format that is convenient and pretty and clear. If on the exam, if you're off by a little bit, I really don't mind. My exams are all based on partial credit anyway, so it's not going to matter that much.
What's the maximum partial credit that you can get?
For everybody else, maybe 80%. For you, maybe 5%. Yes. Yeah, if you change the orientation, yes, that would definitely. And you'd have to, if I wanted to do that, I would just like clearly label this on the problem. This is where the x and the y axis is, and then report it as such. Okay. Here, look, the first, I know that it's below, I know that it's in this half, like to the left of the y-axis, because the x-coordinate is negative on the r. Then the y, so the question again is, it was asked, how do we know that that this is below the x-axis? And the answer is, it really comes down to this right here. The y component of the resultant is negative. So this means that the final resultant is going to be below the x-axis. Okay. All right. Hopefully that clears that up. And yeah, so you can, as we said, we can do these graphically. We can do them using the triangle method, where you actually just plot it and then use triangle rules and things like that. But generally, it is important to know and good to know how to use triangle rules and things like that. That's all. We always start with that just to illustrate where this stuff comes. But we always do that really to illustrate that this stuff comes from trigonometry fundamentally. But beyond a certain point, it gets really hairy to keep doing that. So ultimately, you're going to be using rectangular coordinates more than anything else. But
like when I was doing the problem and I couldn't find the angle below the horizontal, it's because I wasn't doing it like with a ruler and everything. And I
exactly, yeah.
measured that.
You should have actually measured it, literally with a protractor. Yes, do it graphically.
Okay.
To do it graphically, yeah.
I was trying to use the alternate interior angles method, try to find it, and it wasn't working at all.
Yeah. Okay. Okay. Question. Any other questions on that? Okay.
In the test that you said that we have to tell you what the quadrant we're using, is the drawing okay?
Yeah, the drawing is fine to indicate that, yes. Okay. Next problem. Okay, simmer down. We've got a lot to get through today. A trolley hoist. You know, I've actually designed a few of these. These are fun to design. You actually have to design, when you're designing like a lifting mechanism, these are actually, you always end up like just over-designing the hell out of these things. Because, well, if they fail, it's really bad because you're lifting something heavy and it's not going to end well. So, anyway. Huh? Yeah, I mean, it's only a couple tons falling down on you. Yep, hard hats. Yep. Well, some of these loads, I don't know if the hard hat's going to do much. I mean, okay, so it won't crush your skull. Your skull will crush you. Joy. Okay. Anyway, so a hoist trolley is subject to the following three forces. Knowing that P is equal to 250 pounds, determine the required value of alpha if the resultant of the three forces is to be vertical and the corresponding magnitude of the resultant. Okay, so I could draw a free body diagram of this, but we basically already have a free body diagram. So instead, I am actually going to solve for alpha. Okay, and I'm also going to take the lazy way out, I think. You'll see what I mean. Okay, so we want a final resultant to be vertical. What does this mean? Vertical resultant. Exactly. This tells me that Rx, the x component of the resultant, is equal to 0. So you always got to be on the lookout, just like in this class, just like in many other classes. It's sort of there's a certain skill in looking for keywords, power phrases, things like that in problems, and that's one of the keys there. Okay, so I'm going to start with the equation. Rx equals, let me just call this, F1, F2, and screw P, I'm just going to call this F3. F1 plus, not F1, F1x. F1x plus F2x plus F3x. Now we are going to have to pay special attention to where the angles are defined from. So this alpha here is defined from the x-axis. So I'm going to for the x component, I'm going to use the cosine for this one. But for this one, the angle is defined off the y, so I'm going to use the cosine for the x component of this. So f1x here is going to be negative 400 times the cosine of alpha. Negative 400 times the cosine of alpha plus 200 times the sine of alpha plus 200 times the sine of alpha plus p, which is 250, which is then equal to 0. Ooh, what a mess. Negative 400, this is gross. You do have to use the quadratic formula?
I did.
Hmm.
You may have a better way to do it.
How did you do it using a quadratic formula?
Well, I squared the cosine and then made it 1 minus sine squared. And then...
I kind of like that. I kind of like, you know what, let me do that. Yeah, I kind of like that. That's kind of cool. I like that. I always love being able to whip out the quadratic formula. Okay, so yeah, let's have some fun. Let's have some mathematical fun today. Okay, so the first thing I'm going to do is, you know what, I don't like all this really annoying big numbers. So, actually these are kips here, but there are kips here, but they're actually just going to cancel out. So right off the bat, I'm going to divide by 200, and I'm going to have negative 2 cosine alpha plus sine alpha plus, let's see, 250 over, actually, you know what, maybe I'll divide by 100. Maybe that'd be a little bit easier. 200's better? Okay. So 1.25? Yeah, 1.25. 1.25 equals 0. Now, what's next? So the next thing I can do is I can say, all right, I can square all of this. Well, actually, I'm going to isolate the cosine term. So sine of alpha plus 1.25 equals 2 cosine of alpha. And then we can square that and square that. And we would end up with, let's see, that would be sine squared alpha plus, let's see, that's going to be 2.5 sine alpha plus 2.25, no, wait, 1.2, 1.56, I can't remember my powers of 1.25. 1.5625 equals 4 cosine squared alpha. However, I remember my Pythagorean identity from trigonometry of sine squared alpha plus cosine squared alpha equals 1. Isn't this lovely? I actually like this. This is really cool. Cosine squared alpha equals 1 minus sine squared alpha. So this would then be sine squared alpha plus 2.5 sine alpha plus 1.5625 equals 4 minus 4 sine squared alpha. Then we can gather like terms and say 5 sine squared alpha plus 2.5 sine alpha equals, that minus 4, negative, actually just minus, yeah, just need to erase this. Oh. Minus 2.4375 equals 0. So what I would do is I would use the Pythagorean theorem, quadratic formula, one of those things. We already used the Pythagorean theorem. I would use the quadratic formula to get the sine of alpha. So basically, I'm not going to work all the way through this, but I would say that the sine of alpha is equal to the whole quadratic formula. Then from that, I would get alpha alpha is equal to the inverse sine of whatever we got from the quadratic formula. And you do have to be mindful that the quadratic formula will give you two different results, one from the positive, one from the negative. So you'll need to do some, I would want to choose carefully to make sure that I get something that's reasonable. For example, if I got an alpha that was negative, I wouldn't want to use that. I want to get something that corresponds to the drawing. Okay, but yeah, once you have alpha, then you can easily get the magnitude of the resultant just by plugging it into the RY equation. Okay, I don't necessarily want to work all the way through that. Honestly, how I would probably solve this is I'd probably just solve this via graphing. Plug it into a graphing utility of any kind and graph it here. But if you don't have access to a graphing utility, you could use the quadratic formula and trig properties like this. But don't worry, I'm not going to ask you to do something like this on the exam. So, anyway, yes. Let's see time-wise. Which one is it? 2.17. Let me see here.
I have a question.
Uh-huh.
Can we solve this like how we solved 2.21 yesterday?
2.2 and breaking it into components, you mean?
Yeah.
Yeah, that's basically what we did. That's essentially what we did. Okay, 2.17. Let me take a look. I don't know if we have time to work all the way through it, but I can perhaps give you some comments on that. 2.17. And note, I will be posting the solutions to these as well. 2.17. Okay, yeah, that's just a simple, straightforward method of components, I think. So I think take a look at the solutions when I post that. If not, we'll look at it tomorrow. Okay. All right. So there's that. I think that's good for going over homework. Now let's move on to the theory for today. Joy. Okay. So, any questions on those homework problems we went over? That makes sense? Okay. All right. So let's look at some new material. Today we're going to talk about exactly what equilibrium is, and we're going to talk about looking at equilibrium both in 2 and 3 dimensions. And we're also going to be looking at breaking. So far we've stuck with 2-dimensional components of forces, but today we're also going to look at 3-dimensional components of forces. So first I want to talk about the nature of equilibrium. We have talked about this a little bit, and we've applied the principles already, but I have not explicitly gone through and defined what I mean by equilibrium. So what is equilibrium? Equilibrium. So fundamentally, there's two types of equilibrium. There are two types of, okay, let's back up. Equilibrium can mean many different things. Depending on the context, depending on what subject you're looking at, depending on what course you're taking, and depending on what industry you're in, whatever. For example, what is the type of equilibrium you have all worked with before? Remember chemistry class by any chance? Remember you can have thermal equilibrium, where an object is at the same temperature as its surroundings, or thermal equilibrium doesn't mean that it's at the same temperature as its surroundings. It simply means there's just as much heat flowing into an object as flowing out of an object. Or chemical equilibrium, if you have a chemical reaction, there's the same amount of reaction moles per second, molarity per second, going toward the forward reaction as the reverse reaction. It's a stable system. Those are examples of dynamic equilibrium, those are examples of dynamic equilibrium, where something is constantly occurring, but it is in balance. Static equilibrium is something we're concerned about. An example of dynamic equilibrium is what dynamic equilibrium is, in general engineering terms, is a system that is continuously having inflows and outflows, but it's remaining at a steady state. So, for example, you could have a tank of water, for instance, where you had maybe a spigot at the top pouring water into the tank, and then a hole in the bottom draining water out of the tank. If just as much water was flowing into the top as flowing out of the bottom, that tank would be in dynamic equilibrium. There is water constantly flowing and moving through that system, but it is retaining its state. It's remaining at dynamic equilibrium. Static equilibrium is the opposite. It is in balance, but there's no motion of particles going on. It's simply a system at rest or primarily at zero acceleration. So at least in terms of equilibrium for our course here, static equilibrium occurs when all forces and torques. Now, I cringe when I say the word torques. I'm trying to use terms from physics to start out with because that's what you're familiar with. The term we use for these is moments, and we'll see that later on, probably next week. But so I kind of cringe when I say moments, but that's okay. Sorry, I kind of cringe when I say the word torques, but we use the word moments instead of torques, but there's a slight difference. But anyway, on an object are in balance. Instead of torques, I will use the word moments. I will use the engineering term moments. So there are two types of equilibrium we need to consider, two types of static equilibrium we need to consider. So one is equilibrium for a point particle. One is equilibrium for a point particle. The other is equilibrium for an object, or a rigid body. I should say a rigid body. What I mean by a rigid body, we defined what rigid bodies were in the first class, something that doesn't deform. But in this case, specifically what I mean is something that actually has some size to it, some dimensions to it. A point particle, by definition, there's some, I wish I could remember which text it was. It was one of the ancient Greek, might have been Archimedes or Euler or something like that. Not Euler, sorry. Pythagoras or something like that. One of their seminal works in geometry starts off with a rigorous definition of what a point is. And the book starts off with saying a point is an object with no length, no width, or no breadth. So it defines, actually, I don't know if you've ever heard what the word point actually defined, but that's what it actually means. A point is an idealized abstraction. It's a object with no dimensions. So it has no size. A point particle is just obviously a point. It has no dimensions. So if you remember from physics class, a rigid body, and we'll talk more about this later, a point particle is just a point. A rigid body has a size to it. So if you remember your torques from physics, what do you need to have a torque? You need two things. You need a force and what else? And a distance, a lever arm, right? You need a distance. So in other words, for a rigid body, I will apply a force to it, but it will also have some distance from its center of mass. And this distance is what creates that torque, or what we will call the moment. And we'll talk about this more in detail later, L and F. So that's what creates the torque. However, a point particle has no size. Therefore, no moment arm. If a point particle has no size, by definition, it cannot have a moment arm. So this does have size. Thus, non-zero moment arms.
I'm wondering if there's like a force on a atom, like on an atom.
A force on an atom.
Wouldn't there technically be a moment on that
Absolutely, you can certainly have a moment. You can certainly have a moment on an atom. An atom is not a point particle. An atom has size. An atom definitely has size. An atom is made of other things. In fact, you can have. There's an entire concept called what is it? The London dispersion forces. Remember those LDF forces? Those are all based upon sort of momentary, instantaneous dipoles that result from just electrons flying around and momentary unbalances in charge, which creates attractions. And you know what? Please don't tell your chemistry professor. They're probably going to come and whack me over the head with a big chemistry book for bumbling that concept. But anyway, so yes, London dispersion forces. But yes, so yeah, you can absolutely have torques even on the scale of atoms. So atoms can rotate. They have multiple degrees of freedom. They can translate and they can rotate. Is there anything that we're aware of that's actually a point particle? There actually is. Well, okay, I should back up. Ignoring quantum fuzziness. As far as we can tell, there are actually some fundamental particles that have no discernible size, and one is the electron. As far as we can tell, to the limits of our resolution, the electron has no diameter. It is a true point particle. As far as we have ever been able to measure, to the limits of our measuring ability, the electron actually is a point particle. Now, you've studied in chemistry class you've heard the concept spin in terms of electrons. Now, that's a bit of a misnomer. Perhaps that would be better called quantized angular momentum. But we're going really deep into the rabbit hole now, so let's just not worry about that. I'm not talking about true, when I say a point particle, I'm not talking about quantum particles. I'm talking about, engineering abstractions here. Okay, so no moment arm. Let's see. So a point particle can translate x, y, z directions. So we say it has 3 degrees of freedom. D, O, F. You'll hear this term many times in engineering. 3 degrees of freedom. A rigid body can translate or rotate in the x, y, z directions, or it can translate x, y, z directions. But it can also rotate about x, y, z axis. So again, what translation means is the center of mass itself is moving. So this has 6 degrees of freedom. So fundamentally, to be in equilibrium, all of the forces and all of the torques applied to an object have to be in balance. So what this means is, for here, sum of forces in the x direction is equal to the sum of forces in the y direction, is equal to the sum of forces in the z direction, is equal to 0. Here, we have the same sum of forces in the x direction equals sum of forces in the y direction equals sum of forces in the z direction. Oh, that's something funky. Let me knock that out really quick. Sum of forces in the z direction equals 0. So it has the same limitations on translation, but it also has limitations on rotation. So the sum of moments about the x-axis must be equal to 0. Oh, you know what? I want to write it the same way I wrote the other one. Equals sum of moments in the y direction equals sum of moments in the z direction equal to 0. So here we have we can see the difference here. A point particle, which is what we're concerned with for Chapter 2, only has to have the 3 forces equal to 0. A rigid body, on the other hand, also has to balance its 3 rotations. So for a point particle, all of the forces on each of the axes must add up to 0. The components of all the forces must add up to 0. For a rigid body, the moments about each of the axes must add up to 0. And that's the fundamental difference. So what this ultimately brings us, though, is here we have 3 equations of equilibrium. And here we have 6 equations of equilibrium. Six equations of equilibrium. Questions on that? So for an arbitrary point particle, we can take the sum of forces in the x direction, we can take the sum of forces in the y direction, we can take the sum of forces in the z direction, and we can use those to solve for unknown forces. For the rigid body, we can do the same sum of forces about the 3 axes, and we can also do a sum of moments about different axes. And we will see the rigid body example later in the course. That's more chapter, let's see, does chapter 3 have moments in it? I believe it does. Yeah, that's chapter 3 and chapter 4 is where we get into moments. Especially chapter 3. So, I mean, I think we'll be getting into moments tomorrow, actually, if I remember correctly. But perhaps not. I need to look into that. Anyway, but that's the definition of basic equilibrium. So you have already been applying equilibrium whether you realize it or not. You find the components in the x and the y direction, and you can to do it in the z direction, you just add another component. Now, I know that's easier said than done. There's some complexities, and it's a bit more difficult to work in 3 dimensions than 2 dimensions, but that's okay. So questions on equilibrium. Okay. There's one more item I want to go. There's one more item on working with 3-dimensional vectors that I want to go through, and then we'll take a short break. Then we'll work on some example problems. Okay, so 3-dimensional components. We need to look at that. 3-dimensional components. Let's see. Oh, I should mention Freebody diagrams. We've drawn a few of them, but I have not explicitly explained what they are. Freebody diagrams. Okay. These are diagrams showing all forces acting on a point or object. Acting on a point or object. Acting on a point or object. So all Freebody diagrams should have let's see. One, a quick sketch of the object, or this is the least important one. You can be very sloppy with this. Usually you'll just put like a point down or something like that. Just something to indicate that there's an object or point there. 2, let's say all forces on an object including their magnitudes and directions. Yes?
Do you also need like the point application?
Yeah, I'll talk about that. If object is a 2D body, not point particle, include point of application. Of application and distance. and distance. Let's see what else. And that is merely to the point of that is that you need to know where the force is applied so you can properly calculate moments. Yeah, the direction. See here, directions. And then finally, coordinate system, including 0 point if applicable, if you're using coordinates. And positive, negative direction. In other words, which direction is the positive x-axis going? Which direction is the negative y-axis going? If you're gonna write out in some equations sum of forces across the x-axis equals this, well, I need to know which direction is the x-axis. So, just a matter of being clear and everything, internally consistent, etc., etc. Okay, free body diagrams. Okay, so does that make sense? Any questions on that? Okay. Oh, point of note, let's see. Today, office hours normally I do from 3 to 4. Today I'm only going to do from 3 to 3:30. I have something I got to attend at 3:30 on campus, so got to cut that short a little bit. That's okay. But I will be, basically I'll be in the office from, my official office hours are from 3 to 4, but basically what I do is I just, after class gets out, I head up to my office and hang out there till 4. So usually often you can catch me before 3. But anyway, just a note of business. Y'all got this? Okay. Okay. I would like to give a note on point particles. On point particles and point forces. So, remember when we talked about the philosophy of statics and what an engineering model is? This is another engineering model. We draw forces acting on points. In reality, this is another engineering model. This is another engineering model. An approximation. Consider a, let's see, let's say I have a beam. And I hang a chain from this beam. So I have a beam here. It's just a piece of a beam. Then there's a little pad eye here, like we talked about yesterday. And from this, I hang a chain. And to this, I attach a big weight. So, how I would model that is, if I have my beam, I could have my beam line. And I would model that as a point load. A point load P. But in reality, that's actually just a model. What's actually happening, if I really want to drill down deeply into that, I could consider the pad eye. And I could say, in reality, what's happening here is, it's not actually applying a force to the pad eye as a point force. In reality, it's applying force over an area, isn't it? I'm applying a force over a decent-sized area. In reality, what would happen if you actually did apply a point force to an object? Any idea? It would. Yeah, you can think of it this way. Like, imagine if, okay, this floor can support you, no problem, right? Now, okay, it would be hard actually finding a material that would be strong enough to actually do this and maintain a really sharp edge. But imagine you could create some incredibly strong sort of knife balance, imagine like a step stool, but like the bottom is like incredibly sharp knives. And it would have to be made of some impossibly strong material that the edge wouldn't just collapse when you stood on it. But theoretically, ideally, if you had such a system that was balancing your weight upon like some impossible like knife edge thickness, atomic, one atom thick kind of thing, if you tried to stand up on that stool, that thing would just embed into the concrete under your own body weight, wouldn't it? Because the pressure would be so enormously large. Yeah, stiletto heels, yes. Usually that doesn't happen on concrete, but yeah, that happens. I've had that happen on some like wood floors. It's really bad, like some softer wood floors. That can happen actually. But anyway, and also up here, this is also being supported by a point load. Sorry, by a distributed load on the beam. Now, is this wrong though? I mean, is this crude to say, oh, this is a point load that's clearly wrong? No, it ultimately depends on what application you're looking at. If I need to design the entire beam, if this beam is 30 feet long, a point load is actually a fairly good approximation. That works just fine. If I'm designing the pad eye, I actually might want to consider a more complicated system like this when I'm designing just that piece of metal. So whether the point load assumption is applicable or not really depends on your application. You have to have some experience in engineering and judgment to know whether that is appropriate. So again, this is just a model. It's a useful model. Point loads are fine. Point objects actually work just fine for many applications. But I do want to just mention that in general, yes, this is all just models. So one question I often like to ask in my exams is, you know, sometimes I include on some exams I'll include like a free response section, and I'll ask things like, can a true point load exist? Why or why not? And in reality, a true point load can't exist. I can't apply a point load over a single point, otherwise the load would just go right through the thing. When I'm tutoring, sometimes I do some tutoring and tutor even like high school students and stuff. And when I'm tutoring them in physics and they learn the basics of what pressure is, I always like to do the simple demonstration. I have a pencil like this that I usually use. Let me show you. It's one of these blue drafter's pencils with a metal tip on the end. And so what I like to do is I like to demonstrate the concept of pressure by saying, hold up your hand, and they hold up their hand, and I press my palm against theirs and say, no problem, right? And then I'll put the pencil between them and say, let's do this again. Ask them to hold up their hand, and they never were like, no way, I don't want to do that. And I'm just like, what? It's the same force. I'm not becoming super strong. I'm not the Incredible Hulk here. It's just my hand. Why are you afraid? Obviously, intuitively, even a child can realize that that's going to be a problem. I can probably do a lot of damage just, you know, forcing my own hand, with the force of my own hand, simply because of pressure. But anyway, that's the nature of pressure, which you've all learned about many times before. So, let's see. What's next? So that's the nature of point forces. Just wanted to mention that. Finally, let's get to the three-dimensional stuff. Isn't this lovely? So, let's see. How can we talk about this? What would we like to say? Three-dimensional forces. Force in space. So, we're going to talk about a force in space. Actually, let me put a title on this. 3D forces. Oh, where did you go? 3D forces. So I'm going to have, in 3 dimensions, I'm going to have not just the x and y, but now I'm going to add the z. So I'm going to have my x, my y, and my z.
When you give on your tests, so I've noticed on some of the problems, it's completely like flip, but where you would normally put your y or your z, they would be in different positions. Do you give any problems like that?
Generally, I'll keep it fairly straightforward like this, but you should be able to work with generally anything. Okay, so how can we define this? Let's see. Well, we need to consider a couple things. both the force vector and the vector of its line of action. So I'm going to have a vector F. This will be a force vector. What I'm going to call vector lambda will be the unit vector of that force vector. Unit vector along force's line of action. Along the force's line of action. Okay, so let's talk in general here. Let's say down here I have a point A. And A is not a vector, it's a point. It has coordinates AX, AY, and AZ. Point B is another point, and it has coordinates BX, BY, and BZ. Here. Now, the line of force F is going to act along the line from A to B. Let's change this ink color up a bit. Maybe I'll use blue. So the blue line is the line of action of the force. And so I'm going to say that, let's say here, and this is going to be, let's say, lambda AB. So lambda AB is going to be the unit vector of the line from A to B. Lambda AB. And then the force is going to act along that line. So we're going to have F here, like this. So let's analyze this. How would we find lambda? Well, it's simply the unit vector. So first, let me actually define line AB, the vector AB. It's the full vector between A and B, the full distance. It would be, let's say, well, in coordinate form, it would be BX minus AX, comma, BY minus AY, comma, BZ minus AZ. Like so. Then, so that would be the actual full vector. So I would end up with something with a magnitude that's definitely not 1. It would be, it could be very small, it could be very large, just depending on the actual values of these coordinates. And after this, after we develop this theory, I'm gonna actually work through an example, just directly calculating a unit vector for an arbitrary force. Okay. So there's vector AB. The unit vector AB. This would be equal to, well, if we remember from our physics and from our calculus, the unit vector, how will we find a unit vector? The length over the absolute value. So AB over the magnitude? Something over the magnitude. How can we find a unit vector? What do you know about unit vectors? What do you know about unit vectors? Magnitude 1, the direction of the force. It's basically divided by the magnitude, isn't it? That's really all it is, right? So it's just, all this is, it's 1 over the magnitude of AB, right? Remember this stuff? 1 over the magnitude of AB times vector AB. Oh. Times vector AB. Times vector AB. So literally all you do is you get the magnitude of it, and you simply say, and you simply just multiply each of the components. So again, let's see. Let me say that, so again, if I actually, and as a reminder, what would the magnitude of AB equal to? Well, it's just the Pythagorean. So it's going to be equal to the square root of bx minus ax squared plus by minus ay squared plus bz minus az squared, like so. And that is your magnitude. Simple enough. And then, let's say, force F, then, the vector, is going to be equal to the magnitude of F times lambda AB. And there you have it. It's going to be equal to the magnitude of F. In other words, if I had, say, a 10 kip force acting along this line, that would be the magnitude of F. And unit vector AB, I just multiply them together, and I can get the actual vector, the XYZ vector of force F. Simple, right? Okay, so I'll get that, and then I need to, once you get that, finish copying that, then I will go and define theta x, theta y, and theta z. And I want to work through a simple example. Well, actually, let me define theta x, theta y, theta z, and then we'll take a short break. Okay. Okay, y'all got that? Go for it. Okay. So let me define our principal angles. Theta x, theta y, and theta z. Angles of a vector off of the principal axes. Or the cardinal directions, whatever you want to call them. So, let me draw my x, y, z axes here. X, y, z is as shown. And I'm going to show the vector drawn from the origin just for simplicity. So here I have a vector F as shown. And ink color, let's do some red. This is theta x. This is theta y. And this here is theta z. Theta x, theta y, and theta z. So these are the angles taken directly from the force vector to the principal axis. Now, some people are sometimes tempted to say that it's something else. Let me show you this. Let me redraw this. Theta x is not the angle of the projection. What does that mean? Let me show you. It's very tempting to call theta x the angle from the projection, but it's not the angle from of the projection. So again, I have to actually define what I mean by the projection, if you're not familiar. So consider this here. This thing is in three-dimensional space, but if I project a line down to the xz plane, so see it's projected down to the xz plane. A lot of times people are tempted to call this angle from here to here theta x. It's not. Theta x is the angle, again, all the way through space from the force F directly to the axis. This is what I might call theta xz. Or you can call it other names as well. This would be something like theta xz, the angle of the projection of the vector in the xz plane. So do keep that in mind. And then I could define it also with theta y here. Theta y is still just theta y. So again, do not confuse theta x with theta xz. There. Okay, and now I need to work through some equations for this stuff. Like, no, not more equations. Okay, so I need to actually define these. You'll find these equations in the book. Theta x, it would be equal to fx over the magnitude of f. Theta y would be equal to fy over the magnitude of y, or sorry, the magnitude of f. And theta z would be equal to fz over the magnitude of f. Again here, what these mean are fx, fy, and fz are the x, y, z components of your three-dimensional force. And then the relationship between these, the relationship between theta x, theta y, and theta z, there's a cosine relationship. Or, wait, actually, you know what? I am a big liar. Sorry. I'm a liar. It's cosine theta x. That makes more sense. Sorry about that. Cosine theta z. That makes, I was looking at that like, that doesn't look right. Okay. Put a cosine in there. Cosine theta. And let's see, finally, I should probably write down the relationship, the cosine relationship. Cosine squared theta x plus cosine squared theta y plus cosine squared theta z. All of this is equal to 1. That's kind of interesting. All right, so questions on that theory. I would call okay, so the question is, can I explain the difference again between theta x and theta xz? Theta x is the angle from force F directly to the x-axis. Notice here, this is a three-dimensional picture. I have force F, and then I projected it down into the xz plane. Can you kind of visualize that? There is a xz plane here, and theta xz is in the xz plane. So that's what's, so this is like, in other words, if I drew a 2D xz axis, we would have the projection of the force here, and this would be theta xz. And you could call this you could call this different things. You could call this, I've seen this called different things. I've seen it called theta xz. I've seen it called, I don't know, alpha or phi or different. It's totally arbitrary. Theta x, theta y, theta z are pretty consistently defined in different books as off of the xyz axis, but the projection angles are sometimes defined differently. So you can pick your favorite label. It's all the same stuff. All right, other questions on this theory? All right, we can take a short break. When we get back, I want to work through an example of basically applying these equations. Then I have a couple examples from the book that I'd like to work through. All right, go ahead and take a break. We will come back.